Okay, so next step here is to open the software. The software we are looking for is ANSYS Workbench. You want to search for Workbench, and you have to be mindful of the fact that there are two different workbenches. One is Reaction Workbench. We don't really want to deal with this. We only want to use the regular Workbench. Oh, you open the Workbench, and you are going to see the actual ANSYS Workbench. You just have to give it a little bit of time to load. Okay, this is the workbench that you are going to see. On this side, you see a lot of different analysis systems, component systems, and a lot of different things. We don't really need to know all of this, but the only thing you need to understand is that these are complete analysis systems. So each of these modules can do, for example, a fluid flow analysis for you from beginning to the end. What does beginning to the end mean? It means designing geometry, creating the mesh, and doing the simulation. And we're going to go through all of this. I'm going to tell you what all of these means as we go in this tutorial. Okay. So we want to do a fluid flow analysis using Fluent software. So this is the module we are interested in. You want to hold on the left key of the mouse and drag this to your workbench. As you can see here, we have a geometry, we have a mesh, we have a setup, which is the main Fluent software, and then we can see the solutions and the results eventually after the simulation. To do a numeric analysis, you have to make a geometry first. Let's make the geometry. I want to use, if you right click on this geometry, it will show you all of the different softwares they have. I want to use the oldest one, which is a design modeler, but you can use any of this. And you can actually use your own CAD software and export your design here. Okay. So this is the design modeler. What you want to do for this specific project is to essentially create a rectangle that is within a control volume. This rectangle, I'm thinking, can be 1 meters long. As you can see, the scale here is 30 meters. So you can zoom into with the mouse wheel to make your scale smaller. And we want to sketch this smaller. So you see these two options here, modeling and sketching. You click on the sketching. We want to do a two-dimensional simulation. So I'm just going to click on the Z-axis to give me a two-dimensional panel. And then I want to create a rectangle. It is supposed to be a flat plate, meaning that the thickness has to be very small. We want this to be, let's say, 1 meter by 5 centimeters. Okay. You can also check the dimensions, change the dimensions by assigning the vertical and horizontal dimensions here. And you can do this for the horizontal dimensions as well. So as I said, I want to keep the horizontal length to be 1 meters, and the thickness I want it to be 5 centimeters, so 0.005. So you can also move this if you want to, but it is not necessary. And then the next thing you want to do is to design a control volume that is going to be the fluid. This control volume is going to be where the fluid is going to move in. So control volume. You just has to be as big as necessary. We don't really, this big is big enough for our case. Again, this is where this control volume is where everything happens, right? This is the fluid flow. It's going to come in from this side, and then it's going to pass through. It's going to meet this object, pass through this object. There will be a pressure and velocity distribution around this object, and then it will go out from these sides. Okay, this is a very important part of the design when you are doing a fluid flow analysis. We have our control volume. Are the sizes important here? They are important, but for the purpose of this lab, you just want to make them like 4 or 5 times bigger than your actual object. Let's go back to modeling here. We want to hit generate to make sure all the sketches are created, and we want to create a surface using these sketches. So you come to concept here. As you can see, surface from sketches is one of the options. You click on this. You have to select all of the lines. Just one line should do the job as well. And so it did select all of the lines itself. I'm going to generate, and we have our geometry. This is the geometry of interest. One thing you want to do is you want to come here, make sure that you only have one surface body. That's it, geometry design. Let's go to the next step. Next step is meshing. What does meshing mean? Let me double click. Essentially, whenever you are doing a numerical simulation, meaning that you are using a software to analyze the forces, stress, strain, whatever, fluid velocity on this, on anything, you need to divide your geometry into much smaller cells, right? And then the actual solution is going to be done for those cells, each cell individually. Then we are going to do an iteration through all of the cells a couple of times to get an acceptable error. Okay, so this is our geometry. There are a lot of different options here, but we are not going to use any of the options. We want to keep this as simple as possible because it's an introduction to all of these numerical simulations. There is a mesh here. There's coordinate systems. You can choose the material. Again, I am not going to use any of the options, but I want to make sure that we have enough number of cells, because if your cells are too big, then you won't be able to do the simulations. It will diverge eventually. You can see the element size options here. It says 30 centimeters, and this is a little too big. I'm sorry. You want to keep the element size smaller than the thickness. So let's do 2.5 centimeters. Then we can generate the mesh. You can see the meshing progress right here. It usually stays at 5% and then jumps to 100%, as you can see here. So these are the meshes. There are a couple of spots in this mesh which are problematic, like these spots. So if you are an actual CFD engineer or computational engineer, you want to take care of these spots, but for the purpose of this lab, we don't really care about this. And then next step is we have to set up the boundary conditions. We have to tell our software what these boundaries are, and we have to name them. How should we do this? You want to change your selection to edge selection, and then choose each boundary. Right click on it. Then we want to make sure it is chosen. Okay. Yes, this bar is chosen. It is green, as you can see. I'm going to right click on it and then create a named selection. This is where the flow comes in, so I'm going to call it inlet side, or I'm sorry, inlet left. This next one is also where flow can come in depending on the angle of attack. So essentially with the angle of attack is we are going to rotate this geometry technically, right? We're going to give an angle to the velocity vector. So if your angle of attack is 0, it will be directly towards this, the left inlet. But if it's non-zero, if it's a positive, it will come in from this side, the bottom, and the left. And if it's a negative angle of attack, it will come in from top and the bottom and the left. So let's name this one. I don't think I selected that. Yep. Let's name this one inlet bottom. I think I did create a coordinate system mistakenly. You don't really need to have those. Okay. This one we're going to name inlet top. And then this one is where the fluid goes out. So this one we're going to name outlet. But what should we do with this? With this part of the geometry, we are going to select all edges by holding the control button. And then we are going to name all of this wall, which is this is essentially the flat plate wall, right? Okay, you can check all of your name selections here. That's it. We have the mesh. We have everything we wanted to have. We are ready to do the simulation. One thing you have to do here, for whatever reason, they haven't, I guess, fixed this when they were building the software, is that you're going to see that there is an update available for the mesh. You don't really see the check mark. To see the check mark, you have to see the check mark. To see the check mark, you want to right click on mesh and hit update. Yep, so we have the updated mesh, and the mesh is passed through the next module, which is our actual Fluent module. When you double click on the Fluent module, it gives you a lot of different options. If you're using the free version, which is something you can install at home, you can download the student version for this by just Googling ANSYS student version download free, whatever. And we'll let you download for free. If you're using the student version, the number of processors you can use are maxed out at 4. But if you're using one of the ANSYS versions that we have installed in the lab, you can use as many processors as the system has. So I'm just going to increase this to 4 and start the software. Okay, so everything is, as you can see in this panel here, everything is uploaded to the software, imported to here. We just need to create the physics, change the physics, and then run the simulation. Here we have this general tab. In this general tab, you can change the solver, pressure base, density base. This pressure base is the one we want to use. Density base is usually used for compressible fluid flows. We are not going to use this, essentially. Velocity formulation can be absolute or relative to a specific surface or a specific coordinate system that you have to design yourself. And we are doing a 2D planar simulation. There is no symmetry plane or symmetry line here. And we are going to assume that nothing changes with time. So we are already at a stable flow. Next part is the models. So as you can see, this is a multi-physics software. There are different types of physics involved here. You can do a multi-phase analysis that is used like for boiling, with simulating air bubbles in water and whatnot. We don't want to do that. You can do a heat transfer analysis using this energy module. Again, we don't want to do a heat transfer analysis. Or you can do a viscous modeling. And this is what we are interested in. If you double click on that, it will give you a couple of options. InVisit, which, as you remember from your fluid analysis, fluid mechanics, or aerodynamics courses, InVisit is used for cases where you don't want to include the effects of viscosity. But we do want to do that, so we cannot use the InVisit model here. We have to choose from one of these models. The laminar model is for laminar flow. The rest of these are for turbulent flows. And it doesn't really matter which one you choose. Choose whatever works best for you. I'm just going to choose one at random. And I'm not going to change the softwares. I'm going to use SSDK Omega, which is something that was chosen by software by default. All of these other models do exist here, but we are not going to use any of them for this specific simulation. Next step is to choose the material. The only material we're using here is air, and it is already by default chosen here, so we don't really need to change anything here. And then cell zone conditions, we only have one zone, which is our control volume here. It is already chosen. And then boundary conditions. So essentially you have to assign what the velocity, the flight velocity is in all of these inlets, and what happens to this wall, what happens to this outlet. I'm going to double click on this. As you can see, all of the boundaries we have created are imported to here. This interior surface is just the interior surface of your mesh, so we don't really care about that at this point. Let's do the inlets. Let's double click on the inlet left, which is our main inlet. Okay. There are many options. The only option that is open to us is momentum option, because we are not doing any of these other simulations. In the momentum option, where you assign the velocity, you have velocity specification method with magnitude at normal to the boundary, or with magnitude and direction and components of velocity. So for us, since we want to change the direction of the velocity vector, we have to choose one of these two. So magnitude and direction, or components. I'm going to do the magnitude and direction because it is easier. Velocity magnitude, I'm going to use 10, or let's do 50. 50 meters per second is essentially Mach 4.04. It's a very slow flight, which means that we are well inside the incompressible flow field that we want to deal with. X component of flow direction 1, Y component of flow direction 0 essentially means that we are at 0 degrees angle of attack. So the flow is coming in this direction. Let's just start with 0. We don't really need to deal with the turbulence settings here. So we have to set this for all of the other inlets. So, and this inlet velocity comes in all of the inlet velocity has to come in this direction. So I'm going to double click on this, and then magnitude and direction, velocity 50 meters per second, flow direction in the x component of flow direction is 1, y component is 0. Same thing for inlet at top. Okay. For this outlet, it should default to a pressure outlet. If you double click on this, you will see a couple of options, but we don't really need to change any of the options. We can just leave them as is. And for the wall, as long as the type is wall, you don't really need to do anything as well. You can see there are a couple of options, but we don't really need to deal with these options here. It gives you, so let's go back to we are done with the boundary condition. Let's go back to this menu here. We can interface two different meshes with each other, and we can have auxiliary geometries. We can do a dynamic mesh analysis. None of these we are going to deal with. And then we are ready for our solution. In the solution, we can choose the methods. These are essentially mathematical methods that we are going to use in the background to do this analysis. A higher order method is going to give you more accurate results, but it will make your simulation more unstable, meaning that sometimes the error is going to get higher and you won't be able to reach any solution. So you just want to play with this to get the best results possible. And I'm going to leave them as is at this point. Then these controls are the relaxation factors. Again, we don't really need to deal with any of this, but if you want your solver not to march that fast, you want to reduce these two numbers that are closer to 0. Not 0 itself, but closer to 0. And you want to keep this between 0 and 1. And then here is where we actually find the lift and drag coefficient for this specific flat plate. If you double click on the report definitions, you're going to see that you can add a new report definition. We're going to click on this. We have surface reports, we have volume reports, and force reports. For force report, we want to do force report. It has a lift and drag option. I'm going to click on lift. It will also give you the option to calculate lift coefficient instead of lift force, which again, this is what we want to do. You have to choose a vector for this force. As I said, lift is normal, always normal to your flow. The direction of flow happens at 0 angle of attack. So for the flow itself, x is 0, x is 1, y is 0. And if you want a vector that is normal to that, x component has to be 0, y component has to be 1. And we want this calculation to be done for the wall. You just choose this and hit OK, and you have your first report definition. We can actually edit this, change the name as well, make it lift coefficient. And then we need to introduce another one for drag. We're going to name it drag coefficient. Has to be in the direction of the flow, so this x and y is going to be the same as your velocity components. We are going to choose the zone and we're going to move forward. We have the definition lift and drag coefficient. We are going to calculate this, and we are going to while we are running, we are going to see the changes of lift and drag here. Then, whenever you want to do any of the simulation, any numerical simulation is essentially a trial and error. You have to start with an initial guess, solve the whole thing using that initial guess to come up with a secondary guess. Essentially, difference between the initial guess and the secondary gas and the final essentially solutions are called the residuals and are a representative of your error. And then we're going to use that final solution as an initial guess for the next step of the solution, and it will go on and go on and go on until the difference between the initial guess and the solution becomes very small, smaller than your desired error value, and that's when you have converged to a solution. How do we check these? By calculating the residuals, and the residuals are going to be shown to you here in this panel. Let me double click on the residual. So as you can see, for continuity, for the mass conservation, the x momentum, y momentum, and the turbulence factors, turbulent parameters, we have set a criteria of 10 to the negative 3. This means that if the difference between my initial guess and final solution of any iteration is less than 0.001, I have reached convergence. Okay. So we have to start with an initial guess, which happens in this initialization panel. We can do a standard initialization. You have to set the values, or we can do hybrid initialization. I'm going to keep this one as hybrid because it's easier to deal with. And hit an initialize. Gives us in this console, it gives us the message that the hybrid initialization is done. So we are ready to run the calculations. So the calculation, you can see a lot of different options here. Time stepping method. This is, we are not running a transient case, meaning that we are not marching a time, but ANSYS itself is creating a pseudo time setting for us, which essentially means that they are making it, they're running the simulation at different stages that is going to resemble marching in time, which is does not in reality means that we are marching in time. It's just that they want to make this simulation a little more robust and more stable. You don't really need to care about any of this. You can just let them be. This is where we are going to focus on number of iterations. So number of times we are going to take a previous iteration solutions and using it as an initial guess for the next iteration. You can set this to 1000 for now. So essentially our simulation ends either when we reach this number of iterations or when we reach the desired residual for all of the parameters, right? And the second one should be our goal. So if you reach these 1000 iterations and your simulation ends, you want to come back here and change it to 10,000 iterations, essentially. Again, our goal is to reach the desired residual. We are ready to do the calculations. You can just hit calculate, and it will start the simulation for you. As you can see, the drag coefficient is changing. It's because our initial guess was not a very good guess, and it had to change a lot. Let's actually, this is the drag coefficient, and lift coefficient is also changing. But they did reach a stable solution, as you can see. The values we are reading for lift and drag coefficient are somewhat nonsensical. The values shouldn't be this high. But if you check the residual, you're going to see that all of the residuals have reached a value less than 10 to the negative 3, which was our desired residual. So technically we have reached a solution here, but it's not necessarily a correct solution. How can we check for this? You come to these results here, you come to graphics, and then contours, which are essentially heat maps. Double click on the contours. You want to make sure that your interior surface body at least is selected, and you can also change the contours of pressure, density, velocity, whatever you want to see, and you just hit save display. So we are going to have higher pressure in front of this flat plate. You can also select all of them to see the lines as well. Higher pressure gradient here, very low pressure gradients here, which is expected. We can change this to velocity, and then you want to take a screenshot or export these results to put it in your report. Let's check for velocity. Velocity is also something we did expect. But one thing that I'm guessing is happening is the number of cells we have in this thickness area. We only have 2 cells. If we can increase this, we are going to get better results. But essentially, you're seeing the wake, velocity wake that we want to see. We are seeing everything that we wanted to see. So it seems to be correct results. The only problem I can think of is that the lift and drag calculations are not necessarily correct. So we can do some post-simulation calculations here. You can go back to this report definitions and do a force report for lift and drag again. Instead of lift coefficient, we're going to do lift force and see what we are going to get. You can hit compute, and if you hit compute, it's going to show you the force here. So the lift force is negative 14 newtons. Negative 14 newtons is telling us that the lift force is in the downward direction. But we didn't really expect to get any lift force here, because for this is symmetrical effort, for this we should have received 0 lift force. Let's calculate the lift coefficient using this formula. So this is a 2-dimensional case. So this S is essentially just a chord length here, and our chord length is 1 meter. Q infinity 1/2 density multiplied by V infinity squared. What is density here? We can check the operating conditions right here. Reference values, I'm sorry. You can check the reference values right here. These are the values that are going to be used for your calculation of lift and drag coefficient. So density 1.225, area is assumed to be 1 meters, which is fine because the chord length is 1 meter. It's 2-dimensional, so unit depth case 1 meter by 1 meter is 1 meters, 1 square meters. So if you do the calculation, velocity of 50 meters, we have 2500 in the denominator multiplied by 1.2 multiplied by 1/2. Let's say this is 1500, and then we have negative 14 divided by 1500, which means that we are very close to 0. Negative 14 is a very small value for us. Negative 14 lift, which is an acceptable result. This tells me that my lift coefficient calculations are incorrect for whatever reason. So you want to export your lift force and do the lift coefficient calculations from there. You have learned how to do all of this in this tutorial. And you want to make sure to reach out to me if you have any questions, or reach out to your TAs. They are supposed to know everything about this specific lab. Okay, let's see how we can change the boundary condition. We can change the angle of attack. Okay. We have to go to the boundary conditions. Let's say you want the angle of attack of 1 degrees, right? Your x component has to be cosine of that 1 degrees. You can actually do an expression. You can just do a cosine of 1, right? Or you can calculate the cosine of 1 here and put the value here. And this one has to be sine of 1. You want to make sure you select expression here. Again, you can also just calculate the values of cosine and sine and plug in here. You have to do this for all of the inlets. Hit apply. And you also have to come to these report definitions that you have created for lift and drag. Again, let me actually change this whole thing to the lift force instead of lift coefficient. You want to do the same here. For lift, it has to be vice versa, the other way around though. So for lift, x is going to be sine of your degree. Here we can't do expressions, so you have to do the calculations. And for y, you have to use the cosine of your theta. So it has to be the other way around. And that's it. This is all you need to know to do the simulations and then write the reports. Let me know if you have any questions.